we're 95% confident in our method. So now let's actually interpret the confidence intervals. And then today we're going to be working a bunch of examples. And by the end of today, dual credit, y'all will have enough information, or y'all will have all the information you should need to do the homework due Monday. Okay, so when asked to interpret the confidence interval, we can use the following statement. So whatever our percent confidence is would go in this blank. This isn't like a blank to fill something in your notes. This is like a template. We are whatever percent confident that the true, they say population characteristic, really that would be a blank. They're the true mean, the true proportion, the true whatever, is between our lower bound and our upper bound. Of course, lower bound and upper bound would be replaced with our actual values. So make sure we include units for the upper and lower bounds. Like if I'm estimating how large a crowd is, I'm trying to estimate how large a crowd of people would be. And it's between 99 people and 103 people, whatever the case may be. Make sure to include your units. Okay. Let's look at a field house example. We're going to start with this example and we're going to end with this example to an extent. Okay, for a project, a student randomly sampled 182 other students at a large university to determine if the majority of students were in favor of a proposal to build a field house. He found that 75 were in favor. So if we let P be the true proportion of students that favor the proposal, then we want to construct a 95% confidence interval for the proportion of students that favor the proposal. I still haven't got my PowerPoint to work correctly, so let me switch over to Word. I'll work this with y'all. Okay, so let's first get our P hat. What would our proportion be for those in favor? 75 over 182, which is what the 4 decimal places? 4121. Good. So we got our proportion. Now we don't want to just jump in to do a confidence interval with our method. We have to check to make sure we have a large sample. Which means, if we remember right, n times p hat, and then n times 1 minus p hat must be greater than 10. We've got to check each of these. So let's do that. 182 times 0.4121 would be what? $75.0. Is that greater than or equal to 10? Yes. Now we need to check n times 1 minus p hat. 182 times 1 minus 0.4121. What did we get for this one? 107.0. Is this greater than 10? Yes, so it's safe to assume normality. I guess I should put up here safe to assume. Now, what I'm about to do, I'm getting a little bit ahead of myself, but I want to get y'all familiar with the values. So, what we're going to do is we're going to make in our notes a table that dual credit actually has on their Z table. AP does not. But if we make the chart and y'all memorize it, then you won't have to worry about it. It's just 4 numbers. I think y'all can memorize 4 numbers. Okay, so what we're going to do is have a table. I'll change colors here. One column is going to be our level of confidence. I need more room than that. Level of confidence. And then the other one's going to be our critical value. I'm going to call Z crit. Okay, so for a 90% level of confidence, our Z critical value, sorry, not 90, I'm going to start with 80. That's what dual credit has on their chart. And y'all may have to help me out, dual credit, because I don't have them exactly memorized. Is 0.8 on the bottom of your that little table, is it 1.28? So on your Z table, the small chart in the bottom corner. 1.28? Okay. Our critical value for 80% level of confidence is 1.28. For 90%, 1.645. 95%, which is the one we developed yesterday, would be a 1.96 critical value. And the other popular one is the 99% one. And again, y'all may have to help me. It's 2.575. %80 is not as popular. That'll come into play when we get further along into the next chapter. But for the most popular ones that we're going to be dealing with are the 90%, 95, and 99. Okay, so this is just a little table. like I said, AP, I'm sorry, I either have to know how to derive it or memorize the values. We'll try this at sign y'all's chart, so y'all are good. Okay, let's get back to our problem here. We want to create a confidence interval. So what percent confident are we going to be here? What does it ask us to be? %95 confident. So which of our critical values would we use? 1.96. So as a reminder from yesterday, our confidence interval is p hat plus or minus. And yesterday we did a specific interval. I'm going to get us in the hang of generalizing it. Okay, so what is our p hat? What did we find it to be? 4121. So let's plug that in there. Plus or minus. We said our z critical value was 1.96. And that comes the square root of 4121 times 1 minus 0.4121. All over n. What's our n? 182. Okay, now when we do these, what I recommend is calculating this second piece here first. Like once we get our formula written here, I would bring down the 0.4121 and the plus or minus, and then calculate this piece. That way you're not trying to type all of that in the calculator, and yeah. What would you, if you've already calculated it, what did you get for that piece? .0715. Yep. So I know it's election season. If you ever like read the results of an election, especially on the news when it's election night, have any of y'all ever like turned it and just sat there and watched as the results came in? Yeah. So if you look in the bottom corner, it'll say something like plus or minus. Yep. So they don't know the exact results because not everything's been reported. So that margin of error is essentially like a confidence interval. They set a tolerance, and then that plus or minus is this part right here that we just named. Now, of course, if you're reporting it in the media, your level of tolerance is going to be pretty low bound on your error. You don't want a big error. Then people will come at you for reporting false results. Okay, so now once we have our interval simplified, if you will, we still don't want to leave our answer like that. We need to actually break these up into their individual pieces and calculate them. So we're going to have our low piece, 0.4121 minus 0.0715. And then we have the high end, 0.4121 plus 0.0715. When you subtract them, what would you get? 3406. When you add them, what do you get? 0.4836. Okay, so there's our interval. Now let's make a formal sentence, statement. So we're going to say the 95% confidence interval for P is, and then we list our lower bound and our upper bound. Okay, the next page, there's not really too much to talk about PowerPoint-wise, so I'm just going to stay in the notes with y'all and just go through those. And then I'll go back to the PowerPoint here in a second. We have a bunch of formulas, though, to talk about. So when we do large sample confidence intervals for P, of course, we're not going to be just dealing with 95% confidence. Or we could have a 90%, we could have 99%, 98%, whatever. So the general formula for a confidence interval for a population proportion P can be used when these three conditions are met. So the first condition is that P hat must be from a sample proportion from a random sample. Remember back in chapter 2 when we talked about experiment design. We need it to be a random sample, or else all of our statistics are biased. And what did we say yesterday about bias? Doesn't give you a true value. The sample size of n has to be large. This is what that's how we started our problem today. We have to check that n times p hat is greater than or equal to 10. And n times 1 minus p hat has to be greater than or equal to 10. And lastly, the sample has to be selected, or if the sample is selected without replacement, I should say, the sample size is small relative to the population size, meaning it's at most 10% of the population. Which doesn't sound like much, but let's consider, let's say someone's wanting to do a survey here of all high school students. Last I saw, I think we have about, what, 2,200 students? 2,300? I mean, even then, you're looking at surveying to be about 10%. That's over 220 students. I mean, that's still a pretty good size sample. So let's say all those conditions are met. Then the general formula for a confidence interval, and this is where I said earlier I was getting ahead of myself because we were just now talking about the general formula. But it's the one I mentioned earlier. P hat plus or minus our z critical value times the square root of p hat times 1 minus p hat divided by n. Now, dual credit on your formula chart. This value here, they call it E. I'm going to actually make a note here on DC formula chart. They say that this is E and that it's equal to ZC times the square root of P hat times Q hat over N. Y'all see that on the chart? So it's the same exact thing, just written different. I just don't want that to come as a surprise to you when you take the test on Wednesday and you're like, you said these formulas would be on here and they're not. I don't know how to do this. Same concept. Just different symbols. Okay. Now, the standard error portion of our formula is the square root, the whole square root piece. So the standard error would be p hat times 1 minus p hat over n. This is the estimated standard deviation of the statistic. So the other day we called this sigma p hat, didn't we?
Is that supposed to say E equals E credit or C plus or minus?
No, E equals. They call on the dual credit chart, they call that whole value E for error.
Oh.
Okay, now the bound on the error. The bound on the error is the standard error times your Z critical value. So it says it's a 90, they want us to do a 95% confidence interval first. So our bound would be 1.96 times the square root of p hat times 1 minus p hat over n. That's our bound on the error. Which that makes sense. If we go back to that election example like I was talking about, we'll even set it. That's when they give you that plus or minus, that's their margin of error. Yep, that's exactly what that is. That's our margin of error. So this is also called margin of error. But obviously, we're not always going to have a 95% confidence interval. So if we want the bound on the error with any confidence interval, what should I put here instead of 1.96? Yep. This is Z crit. Our critical value. Everything else just stays the same. Okay, let me go to the PowerPoint to make sure we didn't miss anything. Now, I'll pull it up on me. I'll go back because I want to talk about this chart. So, there you go, Will. Okay, so I forgot this chart was part of your PowerPoint, but not on the notes. So this diagram contains 100 confidence intervals for P, computed from 100 different random samples. Now, note that the ones that don't capture our true P are marked with asterisk and are like orange. So these stop short of capturing the true P. If we were to compute 100 more of these intervals, do you expect our results will look exactly like this one? No, probably not. Why? It's random. What's our vocab word that we talked about? Sampling variability. Sampling variability tells us that they're not all going to be the same. So, okay, let's see. We talked about that. That's good, good. Okay, finding a Z critical value. So we already got some practice with this yesterday, and we got, even then, we've practiced this for a while now. If we want to find the Z critical value for a 98% confidence interval, then we could draw a normal curve And if we're 98% confident, that leaves us what percent in each tail? 1% in the first tail, 1% in the second tail. So what I could do is I could look for the top 99%, and that gets me my Z critical value. So you'd look for 0.9900 in your table, and what would you get for that? 2.33. Yeah. I kind of already flashed it up there once. So I wouldn't have flashed it up there. We would have looked in our table, in the middle of the table for 0.9900, and we would have found that that occurs at 2.33. Because, like I said earlier, you can do a confidence interval for any level of confidence. Our most common are 90, 95, and 99, but you can do any. You want to do 98.95, go for it. Okay. Let's look at this next example. This next example is kind of a long one because it talks about 3 different types of confidence intervals, or the three most common confidence intervals. So 95, 90, and 99, I believe. Yes. Okay, so the article, How Well Are U.S. Colleges Run, describes a survey of 1,031 adult Americans. The survey was carried out by the National Center for Public Policy, and the sample was selected in a way that makes it reasonable to regard the sample as representative of adult Americans. Of those surveyed, 567 indicated that they believe a college education is essential. So if we wanted to stop right here and get a point estimate, how could we do that? 567 over 1031. Good. Now, I don't like the estimate they gave, so I'm going to go back to Word so we can get a more accurate estimate. We're just going to do this whole example together. I'll save this whole one together. Well, I'm going to write everything because the PowerPoint, I don't like the numbers they give. They round too much. Okay, so for our point estimate, as Nate mentioned, we can say P hat equals 567 over 1031. So to 5 decimal places, what would that be? 0.54995. Good. So it asks, what is a 95% confidence interval for the population proportion of adult Americans who believe that a college education is essential for success? Now, before we even do the confidence interval, we have to make sure we meet our conditions. So the first condition we want to check for is normality. So we have to check to make sure n times p hat is greater than 10. 1031 times 0.54. All the way up there. There we go. So if I multiply those together, n times p hat, what do I get? Now let's just round to the nearest whole number on these. I mean,
577?
577?
567.
567. Since we're in the thousands, I'm just rounding to the nearest whole number because our sample size is 1,000. So chances are we're going to be there. You just have to make it official. So 567. Then we have to do n times 1 minus p hat. Yes.
If you write Q, what do you have?
Yes, it would be. If you wrote q, it would be q hat. If you're like me, I'd rather just write q hat than 1 minus p hat. Less to write. Okay, so 131 times 1 minus 54995. Is that 464? Yeah. Are both of these greater than or equal to 10? Yep. That one is. That one is. So what's it safe to assume? It is safe to assume normality. Okay, so we meet that condition. We can check that one off. Now, the sample size of 1,031, well, we're saying it's much smaller than 10% of the population size. But if we think about this, how can we just be so sure that 1,031 is smaller than 10% of the adult Americans? So times that by 10, are there more than 10,000 adult Americans here? Yeah, way more. So we meet the 10% requirement by a long shot. And then they tell us that the sample was selected in a way that produces a representative sample. They tell us that in the problem. So since we check off all of our requirements, we can regard this as being a random sample from the population that's less than 10% and normal. which means we met everything to do a confidence interval. So now we can do the actual calculation. Houston, we're gonna go for lunch. So just to remind ourselves of the formula. Okay, well, our p hat's the one that we calculated at the beginning of this example. So 0.54995 plus or minus. I'm doing a 95% confidence interval. So what should my critical value be? 1.96, that's right. 1.96 times the square root of, we got a big square root here. 5 times 1 minus. All divided by 1,030. So again, I recommend calculating your, what we now can call the error. Calculate your error. And what do y'all get on that to 5 decimal places? Zero 0.03037. So there's our, well, it's not our full interval. Now we remember we've got to split it up into its 2 individual pieces. So I'm not going to rewrite it. I'm just going to say subtract and then add. And since we're down to our final answer, let's round to 4 decimal places once we subtract and add. When you subtract, what do you get? 4 decimal places. One, not 6. I'm going to put a colon here so we don't think I'm saying negative. When we add, what do we get? Okay, so if I write this in interval form, 0.5196 to 0.5803. There's my interval. Okay, this piece right here, it's not blanks that we fill in. This is reminding us of our template to put our answer. And in this case, they made it easy for us because they pretty much filled the template in. So a 95% confidence interval for the population proportion of adult Americans who believe that a college education is essential for success is... I don't like y'all too yet. And we just finish our statement here is between. Okay, how can I put this lower value in a percent form? We could say 52. I'm going to leave it as 51.96%.
I don't know we can do this.
Between 51.96 and 58.03%. Now, AP, y'all aren't going to necessarily get the template given to you. It's just one to kind of get you started and working. Hopefully, by the time you do your assignment, you're able to, this just comes natural. I mean, honestly, for dual credit on the test, you don't have to worry about writing a sentence. It'll just say, give the interval. You put it in the interval form, and you're done. So, questions on this part of this example? Okay, let's go on to the next. So this was a 95% confidence interval. Now they ask us to make a 90% confidence interval. What should be the only thing that really changes? That's right. So the only thing that will change is our z-critical value. I'm going to go and even start right, just go and jump into it. 0.54995 plus or minus. I want a 90% confidence interval. So what would my z-critical be for 90%? 1.645. That's what goes here.
That's on the table we made earlier.
Yes.
That's set in stone.
Yes. And it's also on your formula chart. That's where that table actually came from, was y'all's chart. Sorry, not your formula chart, your Z table. Okay, so we have 54995. That's 1 minus 0.54995. All over 1031. So whenever someone gets their error bounds, you know what it is. That's right. 0.02549. And remember, we need to subtract the 2 and add the 2. So at this point, we could even go and break it into, instead of writing a separate step where we show only add, show only subtract, I'm completely okay with y'all going straight to the interval. So when you subtract them, what do you get to 4 decimal places? Okay, so I heard 4, and 4, 5. Okay. What about when we add them, what do we get? 5, 7, 5, 4. What do you notice about this interval compared to the one we calculated first?
About the numbers.
So here's our first interval up here. What do you notice about these two? Get closer to each other, right? Because we want to, we're less confident, which means our interval is smaller. Think about that example that we did yesterday when I asked you, how confident do you feel you could guess my age within 10, then 5, then 1? If you didn't remember the year I graduated, you probably, your confidence would have went down. As I narrowed that range to be less confident. So the percent would go down, but the range kept getting smaller. So as the percent decreases, your range gets smaller. Does that make sense? As the percent decreases, your range gets narrower or gets smaller. Okay. Now let's see what happens if our confidence increases. Good luck today. Hopefully it's not raining at game time.
Hopefully not.
Okay, so now we want to do a 99% confidence interval. For the proportion. So that's on the top of page 8. See y'all later. And we only really have one more topic to get to after this confidence interval. So that'll be in the video. And it's a pretty simple topic. Okay, so again, the only thing that changes in our interval is the z critical value. So if I'm 99% confident, what is my z critical? 2.575. Okay, so let's make our interval. Me too. Okay. We've got all that mess written. The last period we had a little debate about what it was, so we'll see what y'all come up with for this value, for the error.
Teachers, please excuse the interruption. At this time, would you please release all varsity football? Thank you.
We have 399. That's the 5 decimal places. Okay. So now, let's move on to our interval. On the interval, we'll do 4 decimal places. You may be wondering, well, why is our answer at 4 decimal places, but we do all our calculations to 5? Well, that's if you've had any advanced science classes, or even, I don't know, they may even teach it in the academic classes. Significant digits. I don't know if that rings a bell. So basically what it's saying is when you calculate, you want to go one further than what you want your final answer in. So we want our final answer to 4 decimal places, so that's why we calculate 5. What do we get for the lower bound here? 5101. And what about the upper bound? Okay. So there's our interval. Notice that this one, we're more confident, so that means our interval is wider. The more confident you are, the wider the interval. Less confident, yes.
This is still not exactly. If you're trying to find the true value, why would you want to have a wider variable to find? It then gives you more. I don't know. It doesn't really make much sense. In order to narrow it down, I feel like people are smaller.
So right now, I'll admit it does kind of seem counterintuitive. What's going to happen when we start talking about linear regression, we'll start talking about what's called significance. Well, when we start testing for significance, which that's called hypothesis testing, that we'll get into actually in the next chapter, the wider your interval can be and not include the mean, the better. Then you can say, yes, this is significant, this is different than this other number over here. So that's, like I said, right now when we're just constructing them, it's like it doesn't make much sense. But when we start actually using them, you You want a wide interval because then you can say, look how wide this thing is. And the value you're claiming isn't even in my interval.
Oh,
And it's huge.
so instead of
You're wrong.
narrowing it down by there, you narrow it down by.
That's ultimately what we're getting to, yes.
Oh.
Yep. That's ultimately what we're getting to. And then when you start doing like regression and you're wanting to see is there a linear relationship, you look at the slope and look at the interval that the slope could be in, and if zero's in there, then that means there's no slope. The close for correlation, yes. For slope and correlation on regression aren't exactly the same thing.
I just remember doing that.
I think Algebra 1 did a little bit of it. Okay, last topic. It's an easy one. A good one to end with on a Friday. Okay, so before collecting any data, an investigator may wish to determine a sample size that's needed to achieve certain error bounds. So the bound on that error estimate for a 95% confidence interval would be B. Oh, that's interesting. B. B equals, so remember our bound is just the last part essentially. P hat times 1 minus P hat. Oh, I think I wrote that a little too big. Over. Yeah. I wrote that way too big. P hat times 1 minus P hat. Over N. There we go. Okay. Now, if we solve this for N, remember we're wanting to get sample size here, which is our N. I'm not going to work it out algebraically unless y'all want to go through that process. Y'all want to do some algebra? Okay. If you want to, you can do it. Otherwise, we'll just say if you solve for N, you'll get P hat times 1 minus P hat times 1.96 over B squared. Remember, B is your error bound. So now, this is a really specific case for 95%. If I wanted to generalize this, what could I replace in this formula to generalize? This is our Z critical value. That's right. That's all that 1.96 is. This formula is great and all, but sometimes we don't know what P is. So if we don't know what P is, we have a couple of different options. One option would be to do a short little study, try to get a good estimate. Well, is that always possible? No. It won't always be possible to be like, oh, before I do my big study, let me do a smaller one first. So another way you could do it is go on like a historic estimate. Things don't have historic estimates. So we're back to square one. If there's no prior knowledge, we can't do a preliminary study, then the conservative estimate for P would be 0.5.
Just because I understand the words.
And then also, remember when we multiply decimals. Like if I started with 0.1 times 0.2, that would get me, oh wait, sorry, I need to do P and P hat. 1 minus P, sorry. But if 0.1 times 0.9, that would get me 0.09. So I'm like, okay, let's see, can I get bigger than that? I'm going to do 0.2 times 0.8. Eventually, if I worked my way all the way down, I'd get to 0.5 times 0.5, which is 0.25. And then I just start going backwards again. This gives you your biggest value right there. Does that make sense? So by using 0.5 for P, we're using the largest value for P times 1 minus P in our calculations. Now, on these problems, once we know our formula, it really just becomes a plug fest. So let's look at this next example and you'll see what I mean. In spite of the potential safety hazards, some people want to have internet connection in their car. Determine the sample size required to estimate the proportion of adult Americans who would like an internet connection in their car to within 0.03. So that 0.03 would be that's our bound. With 95% confidence. What would our Z critical value be? 1.96. Good. Okay, let's see. I know my bound. I know Z crit. Do I know P? No. So if no P is given, what do I use? No P given. Use P equals 0.5. So now we have P, we have we have Z critical, and we have B. We have our bound. Just plug it in. N equals 0.5 times 1 minus 0.5 times 1.96 over our bound, 0.03, and we square it.
You would round this to a whole number, right?
We would. Mm-hmm. What'd you get with the decimal on it, though? 1,067.11. Okay. So, how many would we actually have to survey?
68.
Yeah. So we can't, this is the minimum, this value gives you the minimum you can survey. This is our minimum we can survey. So obviously I can't survey 0.11 of a person. I'm not going to just talk to their finger or their arm or their elbow. So that means I have to round up to the next whole number. So round up. Okay, so that means our final answer would be 1,068. We can say adult Americans. I'm just going to say 1,068. You know what? Let's be specific here. Adult Americans. That's how many we have to survey. Questions on this one?
If you're doing it like an actual survey, we have to do a lot more as a non-response. Right?
Yes. Yeah. You would have to keep going and going in hopes that that many respond. Yeah. You wouldn't just pick 1,068 to send the survey to because, like you said, some won't respond. Then you have to keep hoping. You can you can send more out, but then what happens? Your sample size keeps growing. So, yeah, that's just the minimum you can do. Well, Nielsen actually does that. They send out surveys every now and then, and it's like there's $2 in the envelope, $2 bills, and they're thank you. Please respond to this short survey. Keep the cash as a thank you, yeah, basically. I can't remember what. And then the longer surveys, they'll send $5 in there. You know, I don't want to do your surveys. You can keep sending me money. I think I actually, when they put $5 in, I did the survey and I haven't gotten 1 cent. I'm like, dang it. I responded and now they're not on to me now. Okay, next example. If a TV executive would like to find a 95% confidence interval estimate within 0.03 for the proportion of all households that watch NYPD Blue regularly, how large of a sample is needed if a prior estimate for P is 0.15? So if we have a if we have a 95% confidence interval, what would our Z critical be? 1.96. What's this 0.03 represent? This is our bound. And then this 0.5, our P. Plug it in. N equals 0.15 times 1 minus 0.15 times 1.96 over 0.03. We can just do, honestly, we can do 2 on these because if you notice in the one above, you really can't even round to, we can't have decimals in our final answer. We can, let's just say 2 decimals and go from there. 544.23. Now can I interview 0.23 of a person? Nope. So 545 households is what we need here. Okay. Let's look at the next one. I'm going to just kind of breeze through this next one real quick because calculation-wise, it's the same as that first one we did, but I need to make a point on it. So again, we want 95% confidence. So Z critical is 1.96. Our bound is 0.03. And they have cal large of a sample is needed if we have no reasonable prior estimate. If we have no prior estimate to use, we have to use P equals 0.5. When we set up our calculation, 0.5 times 1 minus 0.5 times 1 point, that should be a 96 up there, over 0.03. This calculation should look familiar. So we've already done this calculation once. That's the reason I'm kind of breezing through the calculation aspect. 1,068 households. Now, notice what happened to our sample here. How many households did we need on the other? About 45. Yeah. So the reason we had this one in there, not to get practice with the calculation, but the main reason is that notice a reasonable estimate for P can decrease sample size. I should, decrease, lower, same thing. Decrease sample size. So here we didn't have the estimate, so we had to have a large sample. The previous one we did, we were able to decrease our sample size. Okay, last one. The field sample. A college professor wants to estimate the proportion of students at a large university who favor building a field house with a 99% confidence interval accurate to 0.02. So we have a 99% confidence interval. What's our Z critical here? 2.575. Interval accurate 0.02. That's our bound. And they perform a preliminary study and estimate the proportion to be 0.412. That's our P. Let's find our sample size with this. 412 times 1 minus 0.412 times 2.575 over 0.02 all squared. So if you do that calculation, 4,015.77, which means how many people need to be 4,016. So hopefully I didn't think that last part was too bad.